So today we're going to walk through some exam questions for group theory, okay? So this is for Further Pure Maths 2, and it applies for the AS and the full A level, okay? So this is some good practice. First question, so quite a nice introduction, just looking at some basic stuff such as Cayley tables. We're going to move into some more tricky questions, okay? So for these questions, we're using the Further Pure 2 Edexcel textbook, so it's the official textbook, okay? So you can follow along if you want. This is from the mixed exercise 2, and this is question 2. So it's just an exam question. And what we've got is we've got a set G here, which is 1 through to 13, 1, 3, 5, 9, 11 and 13, and it forms a group under multiplication mod 14. So all it wants us to do for 3 marks is just complete this table. So if you're unsure of how a Cayley table works, remember, for example, we go across here, so 1 and 5, so we multiply and then take mod 14. So 1 times 5 is 5, and then do 5 mod 14. So 5 mod 14 would just give you 5. So that's how they've got that element there. Let's have a look at some other ones. So, for example here, 11 times 3, so we've got 11 times 3, that's going to be 33, and then take 33 mod 14. Well, 33 mod 14, well, what would that be congruent to? Well, that'd be 14, 28, and then what do I need to get from 28 to 33? Well, that's just got to be 5. Okay, so all we've got to do is do this for each element. Now, the nice easy thing we can do here is because this is a set G, and we know it forms a group under multiplication mod 14, what I know is that this row here, so this one here, and then this column here at the bottom, they will be the exact same as the, so it'll be this column here, will just be this one here, and this row here will match here. So this will be 1, 3, 5, 9, 11 and 13. And then going down, this would be 3, 5, 9, 11 and 13. Okay, so nice and easy. And remember, when I go across this row now, it will match this column. Okay, so 11 times 3, so that one there straight away we know that's 5. And let's work across here. So 3 times 5, for example, that'd be 15 mod 14, so that's got to be 1, for example. Okay, so we might be able to work through this a bit quicker. So for example, 9 times 3, that'd be 27. Take that mod 14, so that's got to be 13. Okay, and like you can see here, you can work through this pretty quick once you get into the swing of it. Because once we work out this last one here, so 13 times 3, that's 39. Mod 14, so that will be 11. Okay, so now I've got this row, I can just put it into this column here. So that'd be 1, 13, 5, and 11. And notice how quick we can start cutting down this table. So I'm going to do the same again with this row. Then I'll do the column, this row, and then the column, and then just finish the last few elements here in the bottom corner. So 25 mod 14, so that will be 11. And what you should notice, because this forms a group on the multiplication mod 14, what it means is that it's closed on the multiplication. So every element that I get here should be part of the set G. For example, if I get something like 10 as one of my elements here, I've done something wrong because we know it forms a group. So that's just a nice little trick you can use to help. So my next one here, so 5, 1, 11. So 9 times 5, 45. So 42, so that's got to be 3. 5 times 11, that'd be 55. So that'd be 1 mod 14. And then finally 13 times 5, that'd be 65. Mod 14, that will be 9. Oops, I made a mistake. 5 times 11, 55. Mod 14, that will be 13, sorry, 13. I can't do mental maths. So 13, 9, okay. Going down, so now I can go down here, so that one's got to be 3, that one's 13, and that one's 9. And notice now we've only got a few more to do here. So 11 times 9, that'll give me 99 mod 14. So what will that give me? That'll give me 1. And then 9 times 13, mod 14, that will be 11. That'll be 5 there. Okay, and then I can replace that one there with 1, that one there with 5. So now I've only got 3 more to work out. So 11 squared, 121, mod 14, that will give me 9. And then 13 times 11, and then take it mod 14, that will give me 3. And then finally, this one here will just be what I had here, so that'll be 3 as well. And as easy as that, we've done the Cayley table. Okay, so you don't have to show you working throughout the Cayley table. Just put your answers in. Now, if you've got a graphical calculator, one of the Casio graphical calculators, you can actually do the mod function on it. So these questions are really easy. If you get a question like this, think of it as 3 marks. Nice and easy. Okay, so let's have a look at the next question. So this is from exercise 2b, question 14, and it's an exam question with problem solving. So we've got a set M here, 1, 3, 9, 11, under multiplication mod 16. So first part of the question just asks to show that 3 times bracket 9 times 11 is equal to bracket 3 times 9 times 11. So 2 marks. So all I've literally got to do for this is do the multiplication, but obviously take it mod 16. So 3 times 9 times 11, so that's 99. So we'll do all this mod 16. Well, 3 times 99, that would be 297 mod 16. And what's 297 congruent to mod 16? Well, that would just be congruent to 9. Okay, so that left hand side will be congruent to 9. Now let's do the right hand side. So 3 times 9, that's 27 times 11. Well, that'll give me 297 again, mod 16. And again, this is just going to be congruent to 9. So therefore, 3 times 9 times 11 is equal to 3 times 9 times 11. Okay, so as easy as that. Now part B, we actually have to show that this set here, M, is a group under multiplication modulo 16. 5 marks for it. Now when we're proving that something is a group, we have to satisfy 4 different conditions. So let me just clear this just so we've got a bit of extra room. So the conditions that we need to satisfy are that there is closure for the set. So closure for set. We need to satisfy that there is an identity element. Identity element. We need to show that each element has an inverse, so inverse exists. And then finally, we just need to show associativity. I hope that's how you spell it. I'm very bad at English, so associativity. Okay, so we've got to show these 4 conditions. Now, if you've ever got a set, which is just a few numbers, and you're proving that it's a group, a nice easy way to do it is to do a Cayley table. It makes life so much easier. So, for example, this is on the multiplication mod 16. This will be 1, 3, 9 and 11. So hopefully I'm going to have just about enough room here at the end. I should have done a little bit more room, but never mind. And then it'll be 1, 3, 9 and 11 again. So I'm just going to make it a table roughly. So make sure yours is a bit neater than mine in your exam. Mine's very all over the place here. So let's do this Cayley table. So 1 times 1 mod 16 1, and then you can see what's going to happen here. 1 times 3 mod 16 3, and because all the elements are less than 16 here, what I'm going to get is just I'm going to get those elements themselves. Same thing on this column. 1, 3, 9, 11. Okay, so we're nearly there now. So 3 times 3 mod 16, that would just be 9. 3 times 9, 27 mod 16, so that would just be 11. And like we just did with the previous question, if this is a group under multiplication mod 16, what we'd hope is that each element here will give me another element, because what that will prove is that the closure exists under this multiplication modulo 16. And then 3 times 11, 33 mod 16, so that will give me 1 there. That'll be 16, 32. 9 times 3, we've already done that. We've got 11 there, so that'll be 11 as well. 9 times 9, that's 81. You can do 16 times 5 is 80, so that's got to be 1. 9 times 11, 99. Mod 16, that'll just give you 3. So I'm kind of running out of room here at the end, so hopefully you can just about see. 11 times 3, we already did that, that was 1. 11 times 9, did we do that? No, not yet. Oh yeah, we did. 11 times 9, that's 3. Mod 16. And then finally, 11 times 11, 121. Mod 16, that'll give you 9. Okay, so what we've got straight away is, if you check each row, 1, 3, 9, 11, 3, 9, 11, 1, 9, 11, 1, 3, and 11, 1, 3, and 9. Okay, perfect. What we've got here is that each element in the table is a member of M. So straight away, we've proved closure. So every element, so we'll just do this a bullet point, every element of the table is a member of M. So, because every element is a member of M, what we can say is that this is closed under multiplication mod 16. So it's closed under multiplication modulo 16. Okay, so that's closure done. Give that a tick. Next, we're looking at the identity element. So the identity element, hopefully, is nice and easy to see. And the identity element is just going to be 1. If you take a number, say 9, times it by 1, you get 9. Take 11 times it by 1, you get it itself again. So which element, when you times it with something, gives you what itself again, which is clearly just 1 if you look at how the table performs. So therefore, identity element is clearly 1. So we've proved that the identity element exists. So that's good. Give that a tick. Now we're looking at the inverse. So how do you check for an inverse? So if you look at your Cayley table, what you want to check is when you go across, so if I go across this row here, where do I go across to get to 1? Well, my first one here, I'm literally on this square here, it's 1, right? So where does that match up to? It matches up to 1. So what that means is that 1 is self-inverse. So straight away we can say 1 is self-inverse. So 1 is self-inverse. Let's check 3. So if I go across 3, I've got to go all the way across till I get to here, which matches to 11. So what we can say is that 3 and 11, they are inverses of each other. So they are inverses. So obviously that satisfies the 11 one as well. So we've done that one, done that one, done that one. So let's just check 9 now. Where do we go across? We go across here, and we match up at 9. So straight away we can also say as well that 9 is also self-inverse. So each element of the table has an inverse. So 1 is self-inverse, 9 is self-inverse, and 3 and 11 are inverses. So therefore we've satisfied that the inverse exists. And finally, for associativity, if I do this one under here, well, for associativity, what we know is that for normal multiplication, associativity holds, right? So associativity follows from associativity of the normal multiplication. Of normal multiplication. So what that means is that associativity also holds for this set here. So finally what we can say is that the set M, so the set M, so if I do it in brackets, 1, 3, 9, 11, forms a group. Oops, I didn't want to do that. What have I done? So it forms a group, so let's just get my pen back on. Forms a group. Oh, why? I can't get to that F. So that's actually an F, believe it or not. It's kind of annoying. So it forms a group. Let me just do it over here. Forms a group under multiplication modulo 16. Okay, so that's this question done here. Oh, in fact, actually, we've got to show that the group is cyclic. So we're not quite done yet. Another 3 marks for this one. So what I'm going to do is I'm going to erase everything. I still want my Cayley table. So what I'll do is I'll remove the middle bit, just so we've got enough room. Get rid of all this. So I should have just enough room for this. So, to consider whether a group's cyclic or not, what we need to do is we need to consider the generators, right? So the possible generators for this group. So what you're going to do is you're going to go across each element. So let's just get my pen back. So for example, for this question, what you'll actually find is that, if we just scribble this bit off here, what you'll actually find is that 3 and 11 are both generators. So how do we know the generators? Well, to consider whether it's a generator, what you want to do is test it. So we do 3 squared, and what's this congruent to? Mod 16. Well, 3 times 3 using my Cayley table is 9. So that's 3 squared. Now we consider 3 cubed, and what we're hoping for is that this will give me every element. We don't end up getting stuck in a cycle. The cycle only works when we get through each element. So what we should get is something like 9, 11, 1, for example. So let's test whether what this one will be. So 3 cubed, so that would be 9 times by 3. So 9 times by 3, that gives me 11. Perfect. That's what we wanted. And what we should hope now is that my next one here, 3 to the power of 4, will give me 1. Okay, so let's test this one. So 3 to the power of 4, so that would be 11 times by 3. So 11 times by 3, I get 1. Perfect. That's exactly what we wanted. We know that's a generator. Whereas if you tested this, say, on 9, let's see what just happens when we test it on 9. So 9 squared, so that would be 1. But the issue is now, if you do this now, so this would be 9 cubed, that's going to be 1 times by 9, which then end up with 9. And then if you test it again, so that would be 9 times 9 again, we just end up in 1. So we end up in this little cycle there, so it doesn't work. What you need is to get every element. So it doesn't work for 9. And you can test it again with 11. So we do 11 squared. Just mark that off. So 11 squared, that's 11 times 11, so that gives me 9. And then we do 9 times by 11, so that gives me 3. So 11 cubed, that's 3. And then if we do 11 to the power of 4, what would that be? So that's going to be 3 times 11, which gives me 1. Perfect. So therefore, that's how you know 3 and 11 are both generators. So obviously I've done the question beforehand, but to actually check, you've got to go through each one. So check 1 squared, 1 cubed, 1 to the power of 4, 3 squared, 3 to the power of 3, 3 to the power of 4, and do the same with 9 and 11. And obviously it only works for 3 and 11, so therefore the possible generators are 3 and 11. So there you go. So 3 and 11 are both generators. And that's this question fully done. So if we just quickly clear all this, we'll move on to the final question. So this is from exercise 2A, question 10. And again, it's another exam question with problem solving. And it just says, show that the set of integer valued 2 by 2 matrices form a group under addition. And we may assume that the addition of integers is associative. So that makes it a little bit easier. So let's have a look at this. So again, we have to satisfy a few conditions. So we need to satisfy closure, inverse, identity, and associativity. So associativity. But the nice thing is we can already assume that, so we'll give that one a tick straight away. That one's already been done for us, technically by them, because we're assuming that one's associative. So let's have a look at this in full detail. So what I'm going to do here, I'm going to take 2 example matrices. So 2 example matrices, 2 by 2. So if I say let A1, 2, A3, A4, and let's just do B1, B2, B3, B4, and let's just say all these values belong to the integers. Okay, so they belong to the integers, because that's what we're checking, whether it's whether the set of integer value 2 by 2 matrices form a group under addition. So if we take all these values as being integers, what I can do now is set these up for addition. So that's A1, A2, A3 and A4. And let's add that now to the same, but in terms of B. So B1, B2, B3 and B4. So now let's add these up. So that'd be A1 plus B1. That would be A2 plus B2. A3 plus B3. And then A4 plus B4. Well, we already know integers are closed under addition, so integers closed under addition. Under addition. What we can then say is that, for example, if you add an integer to another integer, it'll always be an integer. So what we can just say is that A1 plus B1, A2 plus B2, A3 plus B3, and finally A4 plus B4 all belong to the integers. So what that actually shows us is that this is closed under addition. So that proves closure. So that's that one done. The inverse, well, if you consider the inverse, so if you've got a matrix A, so A, and I just take it as this one here, so it's A1, A2, A3 and A4. Well, what do I add to this matrix to give me 0? Well, in this case, it would have to be A1 minus A1. That would be 0. A2 minus A2, that would give me 0, and so on and so on. It becomes pretty clear once you've done that one. So the inverse, therefore the inverse for addition, that will be minus A1 minus A2 minus A3 and then minus A4. Okay, you add those two matrices, you'd get 0. So that's clearly my inverse. So that's my inverse. My identity element, well, what do I add to this? So if you've got A plus something, so plus something, if I just call it, I just put it in a box, plus something would give me A again. Well, in this case, for addition, that would clearly just have to be the 0 matrix, right? A1 plus 0 would give you A1, A2 plus 0, A2, A3 plus 0 gives you A3, and so on and so on. So my identity is 0 matrix for 2 by 2 matrices, so that would be 0, 0, 0, 0. And then finally, let's just make a quick comment on associativity. So we can assume the addition of integers is associative, so that helps out a little bit. So if I just quickly erase all this. For associativity now, the addition of integers is associative, so addition of integers is associative. So what we can say from that as the addition of integers is associative, it follows that addition of integer valued two by two matrices will also be associative. Will also be associative. And finally, let's just make a little comment. Associative. So as we've satisfied all the conditions, now we've satisfied the identity, the inverse, closure, and associativity. So because we've satisfied all the axioms, so as all axioms hold, we can say that the set of integer valued two by two matrices forms a group under addition. And there we go. Under addition. I just put a big plus there. And there we have it. So that's the final 5 marks for these questions. So I hope that's been helpful. That's all the questions for this video. I'm going to do another one for group theory because there's still quite a few topics that we can look at for group theory. But I hope this has been helpful. If you're new around here, be sure to subscribe and keep up to date with all further maths revision.